So from last time, we saw the basic definition of the minimal group. Basically, it has this left invariant mean on the L infinity space. So we're going to show some basic property of minimal group. So whenever you have a new property for group, you ask yourself whether this property is preserved under all kinds of group operation. And it turns out the minimal group is pretty preserved under most operation you can imagine. So first of all, if you have a minimal group, then the subgroup are going to be amenable. And suppose you have a normal subgroup, then the quotient is also amenable. And also conversely, if you have a normal subgroup and this quotient are both amenable, then your group is also amenable. Sometimes this is called a group extension. And finally, the amenability also preserved under the direct limit. So these direct limit are basically a bunch of group that's ordered under some direct system, and you take their union. And because for any two group, you have a direct system, they are going to be embedded inside some bigger one. So this union is going to have a group structure. You just define their product and the inverse, pretend them inside sitting, any two elements sitting inside some big enough group. Okay, so you end up with a group that's called a direct limit group. That's also going to be amenable. So we're just going to prove all these facts, and let's start with the first one. Let's prove the subgroup is amenable. It turns out it's actually probably the most tricky one, actually. So to show it's amenable, so let's think about what we need to show. So if you know the G is amenable, so let's let G has a left invariant mean, so be a left invariant mean on the L infinity, little L infinity. We assume our group are discrete. So you want to manufacture a left invariant mean on the L infinity of H. So the tricky part is that your L infinity of H is not inside L infinity of G. Okay, so H is a subgroup of G, so L infinity of H is much smaller. So you have to basically, the idea is that if you have a function in the L infinity of H, you want to lift to a L infinity of G, and then use your left invariant mean on G to return some value. Okay, so that's exactly the idea. So how do you do that? Is that well, because you have a subgroup, then you can always divide your group under this H using the right coset. Okay, so A inside M. So here basically you pick one element A from each right coset. Coset here we do need a right coset. We'll see shortly why the left doesn't work. All right, so you pick one from each right coset, and all of these right coset are going to be disjoint, and your G is basically the union of a bunch of these right coset. And the nice thing about these kind of decomposition, well, even though H may not be normal, you can still do this kind of division. And moreover, for every G inside your G has to be inside some of the right coset. And there's your G actually contain a unique one because the right coset are disjoint. So you can find a unique A inside your representative set, say M. And once your A is fixed, your H is also fixed, so that your G is a product of H and A, okay? So now this is basically giving you an idea how you lift from the L infinity of H to the L infinity of G. So what you do is that for every f inside the L infinity of H, okay, so you define a new function, you want to lift it up to a L infinity of G, so that f of G, evaluate at a G to be just equals to the f of H. That's if your G is decomposed as H times A. Okay, so G is H times A. This decomposition is unique, so this is Fg is pretty well defined. And essentially, you're just telling your function to ignore the coset part, ignore the A part. You only care about the H part. And so clearly, this Fg is going to be in the L infinity of G because the little f is bounded above. So Fg is also bounded above. Okay, so the Fg, this infinity norm, and you can clearly see that's going to be equals to the infinity norm of f. Okay, so your Fg is indeed inside the L infinity of G. And so, well, now you lift your function to the L infinity of G. Now you can apply the left invariant mean on the L infinity of G. So let's let n of this f to be the m of the Fg. Then clearly you have the following. So first of all, this n is going to be linear. That's fairly clear. This operation from f to Fg is going to be linear, and m is linear. n is going to be positive because every positive function, if you have f greater than or equal to 0 in the L infinity of h, your fg only takes some f of h, so that's still going to be positive. So your fg is also positive, so your m of fg, and being a positive is a mean, so that's also positive. Okay, so maps positive to positive. And n is going to be a mean because n of 1 is equal to 1. That's just because if you lift the 1 to g, that's just equals to the constant 1 on g as well. Okay, your one function only returns 1. All right, so basically I just need to check is also left translation invariant. To show that, if I consider n of the left translation of h by some f, okay, that's by definition is m of the I lift this left translation function onto g. Okay, so let's do some computation on the side. Okay, so let's do it here. So let's just consider for some g is equal to some k times a. Here k is in h. A is some representative. And let's just evaluate my function, this lift of the left translation at g. So by definition, this is left translation this entire function. Evaluate, I only care about the h part, so this function at k. So by definition, this is f of h inverse of k. And on the other hand, you can consider the left translation. You pretend this is a function fg. Okay, you pretend it's the left translation of your function evaluated at g. So this is the fg evaluated at h inverse of g. Well, but f inverse, h inverse is just h inverse times the ka. And you see this h inverse k is going to be inside h, and your a is inside m. So this is the decomposition of this element, h inverse g. All right, so the lift only care about the h part. So by definition, this is equals to the f of the h inverse k as well. And you see they're the same. Okay, so the whether you lift in the beginning or lift afterwards, whether you do the translation, then do the lift, or do the lift, or do the translation, it doesn't really matter. So this is equals to the m of the left translation of the fg function. And your m is left invariant, so this is the m of fg, which is just equals to the n of f. Okay, so n is also left invariant. And you probably notice here from basically this calculation why we need a right coset, we cannot do the left coset. All right. Any case, the next thing I want to show that if you have a normal subgroup, then the quotient is also amenable. That's going to be much easier. So if you have n normal, you just let Q to be the canonical quotient map, okay? And so if you have a F inside the L infinity of the G mod N, you want to lift it to an L infinity function on G, so that should be quite clear to you. You want to do the composition, so you let Fg to be F composed with Q, so that's going to be inside the L infinity of G. And you just now define your left invariant mean by applying the m to the composition. Okay, so the fg. Okay, this is going to be a left invariant mean on the quotient. Okay, or on the L infinity of the quotient. Okay, so and I'm not going to check the detail. It's pretty clear. Okay, they're basically the same idea. And thirdly, I want to show that if you have a normal group and its quotient are both amenable, then you can extend the group extension is also amenable. So let's let M1 and M2 be left invariant mean on the normal group and your quotient G mod N. Okay, and so basically you want to say for every F inside the L infinity of G, you want to kind of manufacture some function that's on the L infinity of N and on the L infinity of G mod N. And you want to make sure they satisfy a bunch of nice things on their invariant and their translation. So what you do is that let's just write down the definition first. So let's let this big f of x, okay? So essentially what I do is I left translate my f, and I pretend this is a function on n, okay? And I now apply my the mean on n, okay, because I have something inside the L infinity of n, okay, I can apply the m1. The reason this function is nice is because of the following. So let's see, for every xn equals to yn, suppose x and y are the same in the quotient, then this essentially by the normality, you can always find n inside n so that the x is n times y. So what happens if you want to evaluate fx? Okay, so this is the m1 of the left translation by x, but it's also the left translation by n times y. So it's ln ly of f restrict to n. You can pretend this is the ln of this restriction function because n is already inside the normal subgroup n. Okay, so because your m1 is left invariant, so now this left translation by n just disappears. So this is n1 of the ly of f restrict to n, which is just equals to the big F of y. Okay, so essentially your function, this big F, is going to be constant on each of these cosets. So because they're constant on each of these cosets, it just factors through this quotient. So f, basically you can pretend it as a function that's called f bar inside the L infinity of G mod n, okay? So you can pretend it's a function in there. And now let's just define m of my f to be, I construct the big F and I pretend it's inside the L infinity of the quotient, and I apply the mean on the quotient. So that's the m2 of the f bar, okay? Your m is, you can basically check, is clearly a positive linear function because all the steps in here are going to be positive, preserve the positivity and linearity and so on. And if you do the left translation of this little f, you basically left translate your big F by x, the same x. And when you do the quotient, you're basically translating by the xn, the x inside the quotient. And because m2 is also now left translation invariant, they give you the same mean basically. Okay, so this is going to be a left invariant mean. You can do the calculation yourself. Okay. And finally, we want to show that the m are going to be close, the meanability is going to be close under taking direct limit. So the last one, so I have for each of these G alpha, I have a left invariant mean, let's call it alpha, m alpha, be left invariant mean on each of these G alpha. So what I can do is that, well, I want to manufacture that something that's kind of invariant over bigger and bigger sets. So if I let m alpha bar evaluate at f, so here say f inside the L infinity of their direct limit, I can manufacture something that's invariant over G alpha by just restricting my f to the G alpha. Okay, so this is going to be left invariant by translations in G alpha. So let's just say left invariant by G alpha. It's not left invariant by the entire thing G yet, but it is invariant by a set G alpha, and we know the union of these G alpha is going to be the entire thing. So basically, I want to say, well, can I make it bigger and bigger? Okay, so let's let the following. So let's let big M alpha to be all the M inside M of G, so that M is invariant under translation by the G alpha, and I know this M alpha bar is going to be inside each of these big M alpha, so they're not empty. Okay, so I have something that's non-empty, and so first of all, this M of G, all the mean. Okay, so I want to show that each of these, intersection of these M alpha, that's just basically invariant under all of them, that's going to be non-empty. So hopefully one of them, there's some mean inside all of these M alpha. So I need some kind of intersection non-empty. So one way to do that is using some compactness. So let's first of all observe a lot of these sets are going to be compact. So first of all the means, I know they're inside the dual space of G, and because they have norm 1, so that's in the closed unit ball, okay, the dual space of that. So that's going to be a weak star compact by the Banach log rule, the closure basically. All right, so this is because they're weak star compact, and your M of G, that's also a weak star compact. You can check it's closed in the weak star topology. If you take a weak star limit, the weak star limit, well, it will preserve the left invariance for sure. Okay, so you have a weak star compact set. All the means are weak star compact. And each of these M alpha is also weak star closed. Okay, M alpha also weak star closed. That's also pretty clear. You take the weak star limit again. All right, and I just basically need to show they have the finite intersection property. So let's let for every alpha 1 up to alpha n, and I consider the intersection of the m alpha I, okay, I go from 1 to n. This one, well, because your G is a directed system, okay, so that just means there exists some alpha, so that the G alpha is going to contain all of your G alpha I, okay, the union of G alpha I going from 1 to n. So if you think about if a mean is invariant under G alpha, then it's certainly invariant for each of these G alpha I. So your intersection, each of these finite intersection is going to contain the M alpha, which is also non-empty. Okay, so your M alpha is going to have this finite intersection property. So by some topology magic, you know the intersection of all the alpha of these M alpha are non-empty. Okay, so that's non-empty. So you can pick some M inside the intersection of M alpha. Because this M is inside all of the M alpha, so M is invariant under all the G alpha, because your entire direct limit is just basically the union of these G alpha, so M is also invariant under the translation by G. And your M is, because each of these M alpha is inside the M of G, so M is automatically a mean already. All right, so basically now have a left invariant mean, so your direct limit is also amenable.